In the previous lesson, I discussed the three forms of heat transfer: conduction, convection, and radiation. In this lesson, I want to return to radiation, more specifically, radiant energy. I want to tell you something about the relationship between the frequency of a wave and the temperature of the substance emitting it. Mathematically, F proportional to T, which says that the frequency of emitted radiant energy is directly proportional to the absolute temperature of the emitter. Frequency here refers to the peak frequency, corresponding to the most intense radiation emitted, hence the bar over the symbol for frequency. And temperature here is in kelvins, not Celsius or Fahrenheit. You won't need these details unless you're solving problems. The important point is that the frequency of radiant energy is directly proportional to the temperature of the source. That says a lot. Consider a light in a dark room. With no current in the bulb, you can't see it. The radiation emitted by the filament in all parts of the bulb is below your threshold of vision, called infrared. Now gradually apply some current to the bulb and increase the temperature of the wire filament. You see a dim red. Make the wire hotter and the red turns to a bright orange, then yellow, then a jumble of frequencies that blend to produce white. A white-hot filament is hotter than a red-hot one. The higher the temperature of the emitter, the higher the frequency of radiation emitted. This is yum information. The proportion of F to T is applied to today's infrared thermometers. Just point it to an object and the device converts infrared radiation to a temperature reading. When you're taking somebody's temperature with one of these, think of F proportional to T. The colors of visible radiation range from low-frequency red to high-frequency violet. Radiation of higher frequencies than violet, ultraviolet, is beyond human vision. Likewise, radiation of lower frequencies than red, infrared, is also beyond human vision. So humans can't see infrared or ultraviolet, but many other creatures can. Different strokes for different creature folks. The fact that all objects continually emit radiant energy is quite astounding. And here's an interesting question. Why don't objects emitting such energy become cooler as a result? The answer is also astounding, because objects emitting radiant energy also absorb it. Objects are both absorbing and emitting radiation all the time. If an object emits more than it absorbs, it becomes cooler. If it absorbs more than it emits, it becomes warmer. Whether an object plays the role of net emitter or net absorber depends on whether its temperature is above or below that of its surroundings or of other emitters in the neighborhood. A hot pizza outside on a winter day, as our buddy Dennis McNellis shows, is a net emitter. The pizza cools. The same pizza in a hotter oven is a net absorber. It warms. I want to say one more thing about absorption. Although you and your friends may have different colored eyes, all eyes have a black pupil where light enters. Why black? It's because light that enters becomes absorbed inside. None reflects back through the pupil. This is nicely demonstrated by my former student, Helen Yan. We see Helen when she first took my physics class at City College. The hole in the box looks black, even though the interior is a bright white. Almost no light that enters the hole after multiple internal reflections comes back out. And here we see Helen more recently showing the same box. Helen is one of my merit badges in teaching. She has since become a rocket scientist and monitors hotspots on Earth's surface via infrared photography from satellites in space. She is also a part-time physics instructor at City College of San Francisco, teaching the same course she took for me years ago. A big yum to that. In this brief lesson, there's scarcely time to talk about how radiant energy gets through the glass in a florist's greenhouse. Glass is transparent to visible radiant energy, but once absorbed inside, re-radiation occurs at a frequency proportional to the interior temperature, certainly many, many times lower than the temperature of the sun that produced the incoming energy. Radiant energy of this lower frequency finds the glass opaque, unreceptive to transmission. The energy is trapped in the greenhouse interior. good for florists, but not so good with greenhouse gases in the atmosphere, which similarly trap heat energy in the Earth's atmosphere, so temperature builds up. This happened some 4 billion years ago with planet Venus. Carbon dioxide built to a tipping point, where runaway warming produced a surface temperature that melts lead. Climate change here on Earth is controversial at this time. I have one question I don't hear put this way. How could the tons and tons of carbon dioxide that humans have deposited into the atmosphere not contribute to global warming? Back to the pupil of the eye. When you take a flash photo of your friends, you often see their pupils not black, but red. What is the explanation for the red pupils with flash photography? Until next time, good radiant energy.